hello students, again I am your physics sir Dr. Orko Chaudhary. I have come with a new topic in quantum mechanics that is called as the experimental verification of de Broglie hypothesis. Experimental verification of de Broglie hypothesis. Experimental verification of de Broglie hypothesis. Okay, so you know that what is de Broglie hypothesis? De Broglie hypothesis tells that any material particle moving with a velocity v can be represented as a wave of wavelength lambda given by h by the momentum of the particle. So you have to now experimentally verify it. So this was verified by the scientist Davisson and Germer. Okay, Davisson and Germer. Davisson and Germer in the year 1927. Okay, called the Davisson-Germer. They did the Davisson-Germer experiment. Okay, they did the Davisson-Germer experiment. C.J. Davisson and L.H. Germer. In the year 1927, they did the this Davisson and Germer experiment. Okay, they actually did it accidentally, but it was a great proof that it proved the it proved the de Broglie's hypothesis. Now they got Nobel Prize for this. It was such an important discovery that they got Nobel Prize for this. In fact, all these quantum mechanics discoveries, all of this you have done for Compton effect, they got Nobel Prize. For Planck's hypothesis, Max Planck got Nobel Prize. For this de Broglie hypothesis, de Broglie got Nobel Prize. Okay, so what is this actually? Now, this consists of an experimental apparatus. Okay, how does the experimental apparatus look like? It looks like this. It has got basically a filament. It has got a filament like this of a very low tension battery of low tension, that is 6 volt or 12 volt batteries here. Okay. Now what happens is that basically here thermionic emission happens here. Thermionic emission happens here. This is a voltage. Now this is made up of tungsten. This is made up of tungsten. This coil is made up of tungsten. Okay. Now and this is actually coated. A coating of barium oxide is given. Barium oxide coating is given. Why is this barium oxide coating given? Barium oxide, its work function is very low. Okay, the work function of barium oxide is very low. Okay, so what is thermionic emission? So because of this voltage, what happens? Tungsten has got high resistance. Okay, tungsten has got high resistance. So because of this high resistance, so current passes through it, and because of this high resistance, a lot of heat is developed, and because of this heat, what happens? Electrons are liberated, and work function is very low. Okay, electrons are liberated from heat is developed here. Resistance is high. Okay, so resistance high means by that I square RT formula, Joule's law, heat will be liberated. Okay, and so because of this heat, because of the thermal energy, the electrons will be liberated here. Okay, now here there is a cylinder here. Okay, there is a cylinder like this. There is a cylinder like this, and there is a with fine hole, cylinder with a very fine hole like this. Cylinder with a very fine hole is present here. Now what is this cylinder? This is actually connected to a high tension battery. Okay, this cylinder is connected with a high tension battery like this. Say it is connected like this with a high tension battery. High tension battery, it is connected. Okay, so what happens when it is now it has got high volt. Okay, so I mean basically this acts as an anode and this as a cathode. Now electrons are liberated from here because of thermionic emission. So electrons are liberated. Now after liberation, electrons will be generally scattered. Now since they are finding a high voltage here, so electrons will be attracted towards this high voltage, positive voltage. They will be attracted. Okay, now so electrons will come here, and through this very this narrow, through this narrow space, okay, with this narrow fine hole, the electrons will pass. Okay, the electrons will pass from this. Now they will go like this, and here you have a nickel crystal. Okay, here you have got a nickel crystal. Okay, here you have got a nickel crystal. So electrons will come here and be the beam of electrons will come, right? The beam of electrons will come and they will be reflected like this, and from here they will be basically scattered in all directions, and here there will be a movable detector like this. There will be a scale. There will be a movable this is a scale. Okay, and this will be a detector here. This will be a detector. Movable detector. This will be a movable detector. It can move along this line, it can move. Okay, and this is connected to a galvanometer. This is connected to a galvanometer like this. Okay. So this is basically the experimental arrangement. Okay, Achha, now this is a galvanometer. Okay, so now what happens now? Here this is the accelerator. This is high tension battery is here. High tension battery is here, and voltage varies a lot from say from 30 volt to many say 100 volt. The voltage varies. So now what happens? The electrons are accelerated because of this high voltage. The electrons will be accelerated with a high kinetic energy. They will be accelerated. Okay, and they will hit the nickel crystal like this, and ultimately they will be scattered. I mean they will be reflected here in this. This angle is given as phi. Okay, this angle is given as phi. So first the experiment was performed. The experiment was performed at different accelerating potential. The experiment was performed at different accelerating potential. Okay. So now what will happen is that you are seeing that a different accelerating potential was I mean the potential is increased. Okay, the potential is increased, but you see, but significant intensity of electrons was observed. Significant intensity of electrons was observed at 44 volt to 68 volt. Okay, 44 volt to 68 volt. Now what happens here is that, see here, the electrons are coming and getting reflected here like this. Okay, now I mean this is rotated. Okay, and and the acceleration voltage is also changed, right? So now what will happen, the electrons will come here, and the more the electrons, the more will be the galvanometer deflection. From that only you can understand. And intensity is nothing. Intensity of electrons is what? Intensity of electrons, okay, is proportional to the number of electrons. Okay, intensity of electrons proportional to the number of electrons is proportional to the galvanometer deflection. Okay, proportional to the galvanometer deflection. So now what happens that it is seen that between 44 volt to 68 volt you are getting some appreciable deflection. Okay, the best result comes in between this area, and but significant intensity of electrons was observed between this, and the best result is obtained. The best result is obtained at 54 volt. Okay, best result is obtained at 54 volt and 50 degree. 54 volt and 50 degree. That is, you see, suppose this angle is 50 degree. Suppose this phi is 50 degree. Now suppose your the detector is here at this region. Here if you see the galvanometer shows very small deflection. Here in this region, if you show very small deflection, just like you imagine your half deflection experiment we have done in the lab. The galvanometer shows deflection. Okay, the deflection is very small, so 1 centimeter or 2 centimeter like that. Here very small. At 10 degree this angle, it's very small. 20 degree very small. 30 degree very small. 44 degree gradually it increases. It says 10 centimeter like that. At 50 degree and 54 volt accelerating potential, the deflection is the maximum. That is, say it is 16 centimeter like that. Okay. And here if you plot a graph, here if you plot a graph of, that is, this intensity of the electrons, if you plot a graph of intensity of the electrons to phi, what will you see is that you will get a distribution like this. This kind of graph you will get. This kind of graph you will get, where this is the maximum, that is, this is 50 degree, Okay. So this is the thing. And another graph, if you if you plot another graph of say uh, I if you plot a graph of intensity versus the this voltage, that is say kinetic energy EV. Okay, there what will you get? There you will get this kind of graph like this, like this is EV, kinetic energy is EV. So if you plot a graph here like this, so you will get this kind of graph, where this is the maximum, that is this is for that theta is equal to 50 degree, and this voltage you are plotting the kinetic energy here, this is 55 volt, and here gradually this will increase 45, and then this is say 35, this is say 65, this is say 75, like this. Okay, so now I mean this is a very interesting thing. This is a very interesting, why I mean this kind of graph I versus phi, why this kind of graph will this kind of I mean this kind of graph will come, that is this kind of distribution will come. Means this is, if you consider the electron as a particle, if you consider the electron as a particle, then you will I mean if you consider the electron as a particle, then it is scattered in all directions. So if you move the detector in all directions in this way, you will get the same deflection everywhere. Okay, but this doesn't happen. This deflection is maximum only in a particular region. It is maximum only in a particular region. There is a peak. In other regions there is nothing. And another very striking observation is that another very striking observation, number 2 observation, is that if by some technique, only one electron is emitted from the filament, okay, only one electron is emitted from the filament, then also it shows the same I versus phi graph, that is this graph it shows. That is also very strange. Only one electron is emitted from the filament, only one electron, not a beam of electron, only one electron is emitted from the filament. So what will happen if one electron is emitted from the filament? So definitely the one electron, it will not show a the, like wave there kind of thing. It will produce a deflection. Okay, it will produce a deflection, but no, this is not the thing. Okay, so what is happening there? Here also the for a single electron also you are getting the deflection, the maximum intensity, that is maximum deflection at 50 degree only. Now the very interesting part of this is that it's very common thing that it's a single electron. Remember that it's a single electron. Now in a single electron, when it's a single electron will go in a definitely it will go in a single direction only. At one point only it will go, at this point or this point or this point. So at that particular point only we will get maximum intensity. In other points you will get no intensity, that is no deflection, isn't it? Suppose it's a single electron. A single electron will either it will go in this direction, or it will go in this direction, or it will go in this direction only. In other direction it will not go, because it's a single electron. There are no more electrons there. But here you are getting the maximum intensity at this angle only, that 50 degree only. But in other also you are getting deflections. It's not that you are getting completely zero. No, that is so much interesting. That is here that the same thing is happening, that when a beam of electrons is incident, for which you are getting here in that galvanometer, you are getting little deflection. Here also you are getting little deflection. Here little more. Here little more. Here little. Here the maximum deflection you are getting. The same thing you are getting for a single electron also. Now this is very, very, very interesting. Why will this happen at the 50 degree? Okay, it has got maximum deflection, but at other degrees it will get zero. But no, this is not happening. At for a beam of electrons, okay, fine. For a beam of electrons, I mean here I mean they are scattered in different directions. Here suppose there are 2 electrons, so the deflection is less. Here there is 5 electrons, deflection is little bit more. Here there are 10 electrons, little bit more. Here there are maximum electrons, say the 100 electrons, like that. So you are getting maximum, and again here the number of electrons decreases. Okay, fine. Yeah. But what about a single electron? For a single electron, you are getting again the maximum deflection here only. What we have done, that we say how we have done single electron, say suppose you use a filter here, you use a very strong filter so that only one electron is emitted from here, so you are getting again the same deflection at 50 degree only, and other regions also you are getting deflection, but not zero. Now what is the reason behind this? The reason is, this shows that this electron is now behaving as a wave. The electron is behaving as a wave now. Okay, so number 3, the one electron is emitted from the filament. Then also it shows the same I versus phi graph, having maximum intensity at 54 volt or 55 volt, 55 volt, 54 volt. This is say 54. This is 54 volt, and theta is equal to 50 degree. It shows maximum I at 54 volt and theta is equal to 50 degree, and also and also intensities, and also lesser intensities in other angles and voltages, but not completely zero. So what does this prove? This proves that the electron is now behaving as a wave. And wave, what are these waves producing? They are producing constructive interference and destructive interference pattern. This is the same like constructive interference, and here in this region you are getting destructive interference. Okay, now if for a single electron, what would have happened? You should have got a peak only at this position. Other regions it should have been zero. For single electron, you should have got peak only at this position. Other region, or say like this kind of peak only you would have got. In other regions it would have been zero, but no, it is like this only. So this proves that electron is behaving like a wave now. This proves that electron is behaving like a wave. Okay. Electron is behaving this proves that electron is behaving as a collection of waves, not only a single wave, collection of waves. Otherwise, how this interference, constructive interference occurs? Because of superposition. Collection of waves, just like wave packet. Wave packet is what? It's actually a collection of waves only. In some regions it is producing constructive interference, and in some other it is producing, and some others it is producing destructive interference. Some regions it is producing constructive interference, some regions it is producing destructive interference. Okay, so this here basically interference is taking place. Okay, now what happens? Now we'll now prove how this is taking place. Okay, so how is this taking place? So here say at 50 degree it produces constructive interference. Here also it produces constructive interference, but at say these regions, say this is say 10 degree and this is say 90 degree. At 10 and 90 degree it produces destructive, here produces destructive, here produces constructive interference. Okay, so now how this thing happens? So what is happening here? This is a nickel crystal. Okay, now actually how are the crystal planes look like? They look like this only. They are parallel planes like this. Okay, they are parallel planes. Distance between the planes is d. This is d, this is d, this is also d, and you have got atoms here like this. Okay, you have got atoms here. Okay, now suppose say light is falling. Okay, here light is falling, it is getting reflected like this. Again light is falling here like this, it is getting reflected like this. Okay, acha, what I told, constructive interference. So constructive interference, when does interference take place? I told you because of when there is a path difference, that is phase difference, coherence. So you have to find out the path difference here. How do you have to find the path difference? This also I discussed in class. From here you have to draw perpendicular to this ray. From here you have to draw perpendicular to this ray. Acha, this angle is phi. You imagine this one. You imagine this diagram. Okay, phi. This angle is phi. And this is d, and this angle, that is the angle which the ray mixed with the plane, this angle is theta degree, theta. Okay, now if this angle is theta, then this angle will also be theta, this angle will also be theta, and this is d. Okay, so if this is d, so this will be d sine theta, this will be d sine theta, right? So path difference between this ray and this ray is what? Till this, see, these are plane wavefront like this, till this is the same, again from here these are same, this difference is there. So this plus this, that will be 2d sine theta, 2d sine theta. So 2d sine theta. Now 2d is constructive interference. Condition is what? Condition is 2n parts of lambda by 2, 2n lambda by 2, even multiples of lambda by. So you can write it 2d sine theta is equal to n lambda. 2d sine theta is equal to n lambda. This is called as the Bragg's. This is called as the Bragg's law of diffraction. This is called as the Bragg's law of diffraction. Okay, actually this is diffraction due to n slits. Okay, this is actually diffraction due to n slits. You try to imagine it in this way. Okay, you try to imagine it in this way, that is, this is the bending of light taking place. These are the slits. These are the slits. Okay, you try to imagine it like this. Now diffraction is basically nothing but interference only, interference of the secondary wavelets. So 2d sine theta is equal to n lambda. Now here what is the diffraction pattern? How does the diffraction pattern come? You see like this. Like this kind of diffraction pattern comes. Okay, it's wave only. I mean, in Young's double slit experiment also, what happens here? You have got this this slit here, this slit here. So this is a point source. From here one wavefront is emitted like this, then from here another wavefront, from here another wavefront. So these two wavefronts superpose with each other to produce interference pattern. So here also this so basically a wave only produces these kinds of interference pattern like this. Wave only produces this kind of interference pattern. Okay, now here if you consider the central maxima, for it this n is equal to 1. So for that what you will get, 2d sine theta will be equal to lambda. Okay, so now you don't know the value of for nickel you have to calculate now the value of lambda. For nickel, d is given as 0.91 angstrom. Now you know phi. Okay, what is the value of phi here? The value of phi is 50 degree, but you don't know the value of theta. You have to calculate the value of theta. So how will you calculate the value of theta? You see here that if you draw a perpendicular like this, this angle will be phi by 2, and this is theta. So what is phi by 2 plus theta? 90 degree. So this phi by 2 plus theta will be equal to 90 degree. Okay, so phi by 2, 50 by 2, 25. So theta will be 90 minus 25, that is 65 degree. Okay, so lambda will be equal to 2 into 0.91 into sine of 65 degree. Sine of 65 degree. So what will lambda come? Lambda will come out to be lambda will come out to be 1.71, I think. 1.65 into 10 raised to minus 1 nanometer. Okay, 1.65 into 10 raised to minus 1 nanometer. Acha, now what are you doing? You're verifying the de Broglie's hypothesis. How will you do? H by P, right? H by P you will do. Now P how will you calculate? The kinetic energy E is equal to P square by 2m. Now this P square by 2m is how much? Kinetic energy of the electron accelerated by voltage V is what? EV. Okay, P square by 2m is EV. So the P square will be equal to 2m into EV, right? So here 2 into m is what? 9.1 into 10 raised to minus 31 kg into E is 1.6 into 10 raised to minus 19 into V. V is how much? Voltage is 54 volt. Okay, so from here you will get P. I mean P, I don't know what will let me see what will be the value of P. So you calculate the value of P here by doing the square. So if you do H by P, that is H, you know what is the value, Planck's constant. So ultimately this will come out to be 1.67 into 10 raised to minus 1 nanometer. 1.67 into 10 raised to minus 1 nanometer. So this lambda from Davisson Germer experiment and lambda from de Broglie hypothesis. Lambda from Davisson Germer and lambda from de Broglie hypothesis. So these two are almost same. Okay, so from Davisson Germer, what it is proved? It is proved that definitely electron is behaving as a wave only in this experiment. And what is the wavelength of that wave? 1.65 10 raised to minus 1 nanometer. And from de Broglie's hypothesis, you know that any particle electron is having a mass and it's moving with a velocity compared to the velocity of light. Okay, so it can behave as a wave. The wavelength of the wave is 1.67 10 raised to minus 1 nanometer. So these two are same. So hence de Broglie's hypothesis is proved. Hence de Broglie's hypothesis is proved here. Okay, and another important thing is there, yeah, that for this Young's double slit experiment also, here you are using light, that is photons. So if you use electrons, then also you will get a little bit different pattern, but you will get interference pattern. Again, if you use, instead of a number of electrons, you use only a single electron also, then also okay, so you will get interference patterns. For Young's double slit experiment, you will get interference pattern for a beam of electrons as well as a single electron. Okay, for a beam of electron as well as a single electron. So your the hypothesis is proved. De Broglie's hypothesis is proved. Okay, I hope you will be able to understand this. If you have understood this, I hope. Okay, if you don't understand, you tell me when I will take the class. Okay, thank you.